Alright guys, this time I'm going to try to record a video on how to solve the quiz. So, since this is the first time, let's hope it goes well. So, let's start with finding the range and null space of this transformation. So, what you would do, you would first of all find your AT, or the matrix associated to the transformation. And in this case, you can read it off of the transformation, and it would be 1, 1, 0. Then for the y coordinate, you would have 1, 0, 1. For the w coordinate, for the z coordinate first, you would have 1, 1, 0. And then for the w, you would have 0, -1, and 1. What I'm doing, I'm just reading the coefficients in front of each variable. And why is that? Well, because if I apply the transformation to the vector e1, the standard vector e1 with 1, 0, 0, 0, what I would get would be 1 in here, 0, 0, and that would give me the first entry of the column vector. 1, 0, 0, that would give me the second entry, which is a 1, and then I would have 0 plus 0, which is 0. And that would correspond to my first column. The same thing I would do with the vector e2 and so forth and so on. Okay, once we have this, we can calculate the reduced row echelon form of this, and what we would obtain is the following. Like any good cooking show, I have everything prepared in the oven already, and from the matrix here we obtain the following. We have 1 and 2 pivot positions right here. So this is a pivot position and this is a pivot position. What this is giving me is that the rank of the transformation is 2, because I have 2 pivot positions. And what it's telling me is that the range is spanned we would call it just R of t, but I'm writing all out, is going to be the span of the column vectors corresponding to the pivot positions. In this case, would be this vector, 1, 1, 0, and then 1, 0, 1, and that's that. We have a basis for the range. Now, since I have 2 non-pivot positions, the nullity is going to be 2. And of course, the number of pivot positions and non-pivot positions add up to the number of columns. That's the content of the rank nullity theorem. Let me write the null space, or kernel of the linear transformation. This is going to do this, we're going to obtain our solution from here. So what we're going to do, we're going to have 2 free variables. So we're going to write this system right here as, let me do it on an aside here. We're going to have x1 plus x3 minus x4 equals 0. And then we're going to have x2 plus x4 equals 0. So what I'm going to do, I'm going to choose x3 equal to a parameter s and x4 equal to a parameter t. And with this, I'm going to write my solution. The solution space is going to be written, or a general solution will be written, and this should have been a 4. Let me change that. Should be 4 here. There we go. And what I obtain then is going to be negative x3, but x3 I'm going to substitute it with s, and then plus x4, which I'm going to substitute with t. So I'm taking this from this equation right here. x2 is going to be negative x4 from this one, so it's going to be negative t, and then x3 is just going to be s, and x4 is going to be t. So I can write this then as the linear combination of the vectors 1, -1, 0, 1, and the ones that have s is going to be -1, 0, 1, 0. And these two vectors are going to span my null space or kernel. So we're going to have the span of 1, -1, 0, 1, and -1, 0, 1, 0. So we have the range, we have the null space. The last thing we're asked to do is to write down or verify the rank nullity theorem for this particular transformation. Well, we have the dimensions of the domain, which is going to be the number of columns in our matrix, is going to be 4. You can also read it from here. You have 1, 2, 3, and 4 coordinates, so 4 dimensions, is going to be equal to the rank of t, which is 2, plus the nullity of t, and that is 2 plus 2, and last time I checked, 2 plus 2 indeed is 4, though some people may disagree. Alright, so this one is a little more interesting. Let me try to draw a few pictures. I have the transformation t that is going to go from R2 into R2. So I have my space R2 here, my domain, and my codomain R2, and I have that the vector, let's call V1, let's call it 1, 2, and V2, let's call it 2, 1. And I have V1 here somewhere, and V2, and my transformation t is sending V1 to E1, and whatever this is, V2 to E2. Okay? So then I'm asked to find the matrix of that corresponding to that transformation. Well, what do I need? Well, first of all, let me write down the definition of this matrix, or the result we obtained, that this matrix has column E1, T of E1, and T of E2. So I need to find out how in the world can I write T of E1 in terms of T of V1 and V2. So what you want to do then is write T of E1, and since V1, V2, or the basis B is a basis, then you can write, there's a unique representation of E1 as a linear combination of V1 and V2. Therefore, there will be, you will have coefficients alpha and beta such that E1 equals alpha V1 plus beta V2. Using the linearity of our transformation, we can break it down into this equation. But I told you that T of V1 up here, T of V1 is E1. So this is just going to be alpha times 1, 0, plus then T of V2 is E2, which is 0, 1. And hence this is going to be just the vector alpha, beta. So that means it suffices for me to find the coefficients alpha, beta that I need to write E1 as a linear combination of V1 and V2. So to do that, all I have to do then is solve the system of equations, in this case 1, 2, 2, 1, and I would have to augment it with 1, 0. That would be to get E1. Then I have to do the same thing for E2, so might as well do it in the same calculation. And what will happen is whenever I do this reduced row echelon form, what I'm going to obtain here is going to be, if I call this matrix A, I'm going to have my matrix, my identity here, and then I'm going to have my matrix AT, which is just going to be the inverse of this matrix. because whenever you calculate the reduced row echelon form of a matrix augmented by the identity, where you're going to obtain, if it's invertible, you're going to obtain the identity and then the inverse. So basically all I need is that, or what I found there is that AT is just going to be the matrix 1, 2, 2, 1 inverse, which I could do in the reduced row echelon form, but it's a lot simpler to use the shortcut formula for the determinant of a 2 by 2, which is going to be for a inverse of a 2 by 2, which is going to be 1 over the determinant, which is 1 minus 4, times, then you put negative signs to the off diagonals, but you do swap the diagonal entries and put negatives. And there's going to be a negative 1/3, so whenever you multiply everything out, it's going to be negative 1/3, then 2/3, 2/3, and negative 1/3. And that is the matrix AT that we wanted. Then if I want to find the null space and the range of this linear transformation, what I want to do is find the null or kernel, the null space of the corresponding matrix. So to do that, I need to find the reduced row echelon form. I'll put it out here. What you would obtain is, well, once you do the calculation, since the columns are linearly independent, you're going to obtain that this is the identity. And then you would have that the null space is 0, because whenever you set the system of equation, or whenever you find the solution to the homogeneous system of equations corresponding to this matrix, is going to be then, is going to have only the trivial solution x equals 0. So that tells you that the null space is 0, and the range hence is the whole of R2, because you have precisely 2 pivot positions, so you span all of R2. And lastly, you have to find AT inverse, which happens to be just AT inverse. And the way I obtained AT was by doing the inverse of this matrix right here, so I don't even have to calculate anything, just copy the matrix. And that's that. We finished within the time I was allowed, and well, I hope this helps, and I hope this is better than me putting the notes online. Alright, until next time, that is that.